The exponential logarithmic identity. Hello everyone. To begin, let's look back at what we have already covered. In our previous subsections, we established that the natural exponential function, f of x equals e to the power of x, and the natural logarithmic function, g of x equals log x, are inverse functions of each other. Now, it is important to remember a fundamental property of any two inverse functions. They essentially undo one another. In other words, if you apply one function and then immediately apply its inverse, you return to your original value. This specific relationship between the exponential and logarithmic functions leads us to a very powerful mathematical tool known as the exponential logarithmic identity. Over the next few slides, we will break down exactly how this identity works, the conditions required to use it, and how it can simplify complex calculus problems. Understanding the identity. Now that we have established that the natural exponential and logarithmic functions are inverses of one another, let us examine the specific identity that arises from this relationship. The exponential logarithmic identity states that for any positive real number x, x is equal to e raised to the power of the natural log of x. To help you understand why this is mathematically true, let us break the logic down into 5 clear steps. First, let us consider the definition of a logarithm. By definition, the natural log of x is the exponent to which the base e must be raised to produce the value x. Second, to make this easier to visualize, let us set up an equation. Let us assume that the natural log of x is equal to a variable, which we will call y. Third, we convert this into exponential form. According to the definition of logarithms, if the natural log of x equals y, then it must be true that e raised to the power of y equals x. Fourth, we perform a substitution. We take the value of y from our second step, which was the natural log of x, and substitute it back into the equation from step 3. Therefore, we replace y with the natural log of x in the expression e raised to the power of y equals x. Finally, this leads us to our result, e raised to the power of the natural log of x equals x. This identity is a powerful tool, but before we apply it to real-world problems, we must first discuss a critical restriction regarding the domain of x, which we will cover in the next slide. The importance of the domain. Now that we have established how the identity is derived, we must address a critical aspect of this relationship, which is the restriction on the variable x. It is important to note that this identity is only valid when x is greater than 0. To understand why, we have to look back at the domain of the logarithmic function. As we discussed in our previous lessons on the characteristics of logarithms, the natural log of x is only defined when x is a positive real number. In practical terms, if we attempt to substitute a negative number or 0 for x, the expression log x becomes undefined within the set of real numbers. Because the logarithm itself cannot be calculated for these values, the entire expression, e raised to the power of log x, consequently becomes undefined as well. Therefore, we must conclude that the identity stating x equals e raised to the power of log x holds true if, and only if, x is greater than 0. Keeping this domain restriction in mind is essential before we move forward to see how this identity is applied in real-world mathematical modeling. Real-world application, mathematical modeling. Now that we have established the identity and understood the importance of its domain, let us explore why this mathematical relationship is so valuable in practical applications. First, consider fields such as physics and economics. In these disciplines, scientists and analysts frequently encounter variables that grow at rates proportional to their own size, a phenomenon we commonly refer to as exponential growth. Because of this natural behavior, it is often mathematically more convenient to work with the natural base, e, rather than dealing with the variable x directly. To give you a concrete example, let us look at complex differentiation, specifically a technique known as logarithmic differentiation. In this process, mathematicians often rewrite a variable x as e raised to the power of the natural log of x by applying this identity. They can transform a complicated product or a power into a simple sum or a coefficient, which makes the resulting calculus operations much more manageable. To see exactly how this transformation is applied in a problem, let us move to the next slide and walk through a step-by-step example. Step-by-step example, rewriting an expression. Now that we have discussed the theoretical side and the real-world applications of this identity, let us walk through a practical, step-by-step example of how to rewrite an expression. Suppose we want to rewrite the expression x to the power of 5 in terms of the natural base e. In step 1, we begin by identifying the base variable. In this specific expression, our base variable is simply x. Moving to step 2, we apply the exponential logarithmic identity that we established in the previous slides. We know that x is equivalent to e raised to the power of the natural log of x. In step 3, we substitute this identity into our original expression. This means that instead of writing x to the power of 5, we replace the x with our identity, giving us e raised to the power of the natural log of x, all raised to the power of 5. Finally, in step 4, we use the laws of exponents. You will recall that when a power is raised to another power, we multiply the exponents together. Therefore, e raised to the power of the natural log of x, all raised to the power of 5, simplifies to e raised to the power of 5 times the natural log of x. This particular transformation is an essential tool for your grade 12 calculus course. It is especially useful when you are differentiating functions where the variable appears in both the base and the exponent, as it allows you to simplify the expression into a form that is much easier to manage. Key takeaways. Now, let's wrap up everything we have covered so far with a few key takeaways to ensure you have a solid grasp of the concept. First, let's reiterate the identity itself. X equals e raised to the power of the natural log of x. Secondly, it is important to remember the why behind this. This identity exists because the exponential function and the logarithmic function are inverse functions. As we discussed at the start of this lesson, they essentially undo one another. Third, we must be mindful of the domain constraint. This identity is strictly valid for x values in the interval from 0 to infinity. In simpler terms, it cannot be applied if x is less than or equal to 0, because the logarithm of a non-positive number is undefined. Finally, regarding its utility, this identity allows us to switch a linear variable into an exponential form. As we saw in the step-by-step example we just completed, this transformation is incredibly helpful when you move into advanced differentiation in calculus. Now that we have summarized the core concepts, let's move to the final slide to discuss some common mistakes you should avoid. Common mistakes. Now that we have covered the key takeaways and seen how to apply this identity in practice, let's wrap up by discussing some common mistakes to avoid so you don't lose marks on your exams. First, let's talk about ignoring the domain. As we emphasized earlier in our discussion on the importance of the domain, a very frequent error is attempting to apply this identity to negative values of x before you ever write down that x equals e to the power of log x. You must always verify that x is greater than 0. Second, be careful not to confuse your bases. In this unit, we are focusing on the natural logarithm, which uses the base e. However, students often confuse this with the common logarithm, which uses base 10. Please remember that the identity x equals e to the power of log x only works if the log refers to the natural logarithm. If you were working with a base of 10, the identity would instead be x equals 10 to the power of log base 10 of x. Finally, be mindful of the order of the functions. While it is true that e to the power of log x equals x, some students mistakenly think that this is the exact same expression as log of e to the power of x. Now, it is important to note that log of e to the power of x also equals x, but these are actually two different directions of the inverse relationship. One is the exponential of a logarithm, and the other is the logarithm of an exponential. While they both simplify to x, they are conceptually different operations.